Yeah, that's it. We are looking at chapter 6, multiple regression models with multiple regressors. So it's like, in a sense, it's just an extension of chapter 4.
Mm-hmm.
Yeah, it's an extension of chapter 4. I think the main issues here will be omitted variable bias, and which is like a problem with chapter 4, because when we look at a single regressor, we have that problem always. So we'll also look at the multiple regression and some OLS estimators and the some assumptions as well. Well, from now we had like up to 3 assumptions, so we'll add some like the multicollinearity assumption as well. So naturally, we will discuss estimation of multiple regression models using R. We'll also illustrate the importance of thoughtful usage of multiple regression models via simulation studies that demonstrate the consequences of using highly correlated regressors or misspecified models. So basically, we'll look at also measures of fit as well. We'll discuss that as well. Yeah, I think that's what we hope to discuss. Yeah, now we'll start with omitted variable bias. So like the error, we have the error term because of the omitted variable bias issue. So in a sense, we want to, because we're not able to control all the variables that are related to that will help us predict well the dependent variable. So that's why we have the error term to capture some of these variables that we are not able to control for. So we have some assumptions in the previous analysis of the relationship between test scores and the class size discussed in chapter 4 and 5 has major flaws. We ignore other determinants of the dependent variable, like the test score that correlates with the regressors. So I think the main problem with omitted variable bias is when it leads to like when it leads to the OLS estimators being sort of biased, then that particular omitted variable is a concern, and we have to consider including in our model's specification. So key concept 6.1 gives a summary of this. Omitted variable bias is the bias in the OLS estimator that arises when the regressor X is correlated with an omitted variable. For omitted variable bias to occur, 2 conditions must be fulfilled, and that's it. The first one is X is correlated with the omitted variable, because the omitted variable is a determinant of the dependent variable. So if these 2 conditions are satisfied, then this particular variable will be considered omitted, and we should consider it in our model. We should include in our model. If not, our OLS estimates will be biased. Together with 1 and 2 results in a violation with the violation of the first assumption, the first OLS assumption, which is the conditional, the zero conditional mean assumption, that is expected value of the error terms given the regressors is equals to 0. So if these 2 conditions hold, then this will not be true. Which in a more mathematically written way, it could be that the estimator for beta 1 hat sort of converges in probability to beta 1, like the pre-beta 1, the true beta 1 plus the correlation between the regressors and the error times the like the fraction of the variance of the error and the variance of the regressor. So like it's saying that this is the derivation of this is explained in appendix 6.1. So this in a sense 6.1 is telling us that if we have an omitted variable problem, increasing the sample size will not solve this problem. And the OVP prevents the estimator from converging in probability to the two parameters, which in a sense will lead to the bias. Strength and direction of the bias are determined by the correlation between the regressors and the error term. So now it's giving an example. So since the example that the textbook use, it's like the test score example. So it's like saying let us think about the bias introduced by omitting the share of English learning students. So here, like in the test score example, we see that what we are looking at the effect of the student teacher ratio effect on the test score. So this was the model we looked at in chapter 4, I guess. So there is sort of an omitted variable bias in this because we are saying that the English language ability, like whether English is a second language or a native language, has some effect on the test score. So omitting that will lead to like a omitted variable bias, because this particular variable, the variable like percent of student learning English, this variable, in a sense it's correlated to the student ratio, and it's also sort of it also correlates to the dependent variable. So omitting it in our model will lead to omitted variable bias, where the student teacher ratio and the percentage of student learning English are correlated. So we have that the correlation between them is not 0, so there is some correlation there. So in using R, we could create this new variable, and then look at the correlation. We see that like the correlation between the student teacher ratio and the test scores, and the correlation between the student teacher ratio and the percentage of student learning English. We could see there is some correlation. So it's like the high correlation we see here, which is like between the student teacher ratio and the test score, is like caused by the omitted variable, like omitting the percentage of student learning English. This could be like an example where you have a district where you have a lot of immigrants. Then in that sense, you will expect that many of the kids in the school, English might not be their first language. So in that case, you'll have a huge number of them that will be studying English, which in a sense will affect the test score. So in this model here, we see what will happen to the beta one, like the estimate of the student teacher ratio, if we include the percentage of student that is learning English. So it's going to be negative, and the coefficient is going to be even larger than the previous one. And this we could easily confirm by estimating the model in R. And that's it. When we estimate the model in R, without including the percentage of students that are learning English, we have the beta 1 coefficient as minus 2.8. Whilst when we include the percentage of students that are learning English, we have it as minus 1.10. Yeah. So these outcomes are consistent with what we expect. I'm not sure whether I'm explaining this clearly, but if someone has any comments or questions.
Good here, I think.
Yeah. Yeah, I think now we could move to the uh, 6.2 multiple regression model. Now, so in a sense, we are just extending the single regression model to accommodate for more regressors. So a multiple regression model enables us to estimate the effect on yi of changing a regressor, like x1i, if the remaining regressors x2i, x3i sort of do not vary, like this ceteris paribus assumption. So in a sense, we have already done this when we are estimating the equation 6.2, sorry, in R. Since like the interpretation is like how the dependent variable will change due to like a unit change in the regressor we are interested in, holding all the other regressors constant. So basically, the interpretation of the coefficient on student-teacher ratio is the effect on test scores of one unit change student-teacher ratio if the percent of English English learners is kept like constant. So like in a sense, we are trying to control for all the other variables that that will affect that are sort of correlated to student-teacher ratio, and in a sense, are also help us explain the conditional mean, the zero conditional mean assumption, which is like the expected value of yi given the axis is equals to beta node plus beta 1 up to like all the regressors that we are considering, like as in the simple regression model. But we have to consider the error term, regardless of how much regressors we consider. There's still some error, and sort of we have to account for that by including the error term in our model. So key concept 6.2 summarizes this. The multiple regression model is yi beta node plus beta 1 x1i up to beta k x ki plus ui, where I is from 1 to n. The designations are similar to those in the single regression model, where the ith observation is the dependent variable. observations on the key regressions are denoted by x1 I, x2 I up to x ki, and u is the error time. The average relationship between y and the regressors is given by the population regression line, which is this. And beta node is the intercept. It is when the value of y when all the x's are 0. And the beta j's are the coefficients of the xj's. Sorry, the beta 1 measures the expected change in y that results from a 1 unit change in x1, right? Holding all the others constant. So in a sense, it just summarizes what I've just said. So we could use OLS to still estimate this model as we did previously. We could use OLS to estimate 6.4. As in simple model, we seek to minimize the sum of the squared mistakes by using the estimates of the beta of B0, B1, or BK for the coefficients of beta 1, beta 0, and such. So we could use OLS to do this, and so the difference between the y I and the predicted y is called the Euler's residual of observation I, which is like ui is equals to yi minus yi hat. Let us jump back to the example to test the. So like we had this we had already estimated this model. The estimated model object is the multi-dot model. As for simple regression model, we could use the summary function in R to obtain the information. So like if we like summary and the model, then the coefficient will have like it will give us the coefficients, and it will give us the standard errors and the t values and the p values. So just for curiosity, like I observed the t values being negative. Is it something like normal, or does it ring a bell or what? If anyone has thoughts on that, will be appreciated.
Yeah, it's normal because we have an estimate here like a negative.
Yeah.
And then when you try to minus 1.1012 divided by 0.380, that actually gives you a t value here.
Of a negative, yeah.
Yeah, and also as you can, when we looking at these kind of normal distributions kind of things, what we can do is we gonna testing about the 1.6, negative 1.6 and positive 1.96, right? And then we're gonna testing this area, right? In this area is a kind of like what is called the rejection region, which means if t value is less than negative 1.6 or more than 1.6 within this area, we can safely say reject our null hypothesis, which is beta 1 is 0. That is the null hypothesis. And in this case, alternative 1 is beta 1 is not 0. So in this case, like STR, in this case, the negative minus 2.5 is we are here. t-value is around here, right?
Yeah.
Which is the totally within the dead rejection region. That means we can reject this null hypothesis, which is the beta 1 is 0. So that means this one is, we can say about the within the less than 5%, we can say that the coefficients of between coefficients between coefficients between the student teacher ratio and the score is less likely to be 0.
Yeah.
Right.
Yeah.
So that's the reason why we have a very small p-value, which means students teacher ratio is highly associated with the score. And then the negative means is that they are actually negative relationship.
Related, yeah.
Which means when the students teacher ratio is up, average English score of the students gonna be going down. The Y is going down, which makes sense to us, because maybe if a teacher have too many students to handle, in that case, there is a less possibility to each students can have a good English score, because a teacher cannot pay attention to that many kind of students. So that's the reason why in the educations, we actually care about the students teacher ratios is as minimum as possible. Like when you thinking about the one teacher should be handle 20 students versus one teacher should handle the 50 students.
Becomes a problem.
So in there, this becomes a problem. So that's the reason why we have a negative one. And then English speaking students ratio is also kind of a negative too. We can also interpret the same way. So it is natural, because that is how estimates goes, that when you always think about that this kind of standard normal distribution curve, and then thinking about the minus 1.96 and 1.96, and then always thinking about that t-value calculated by estimate and standard error, and then that t-value is located within either of these two regions. Okay. So that's the kind of a key. So now we have these two value is definitely less than negative 1.96, which means these two are very significant. At the same time, based on the estimate, we can find that there are all the negatively associated with the English score, right? So
thanks for that clarification.
Please go ahead.
So the model was estimated, and we could see like the test score, the estimates we have, like we have the constant, which is when both the student teacher ratio is equal to 0 and the English score is also equal to 0. We have that to be 86.3, and then we have the coefficient as in here we have. So basically that's the model. So unlike in the simple regression model, where the data can be represented by points, so here by points in two-dimensional coordinate system, we now have 3 dimensions. Look, so that's the plot here. We could see the visualization. We could see the linear connection. We could see that there is the linearity still holds, and the line of the line of best fit crossed through very well. But we could also see that there is some anomaly that can be seen from the plot, like a problem of maybe heteroscedasticity. We see that the dispersion of the regression error meets the distance of observations to the regression plane tends to decrease as the English language learning students increase. So we could clearly see this, which shows that maybe there is a heteroscedasticity issue here. Yeah, I think that was it. This is just trying to give a visual image of this model. But it also tells us that we might have some limitations as the regressors increase. It might be difficult to be able to visualize it, because now we have like 2 regressors, so it's possible to visualize it. But when we have more than 2, and wanting to visualize it like this might be complicated or almost impossible. So now we look at measures of fit. So the measures of fit in multiple regression, we have the common statistics are the standard error of the regressors, which is in a sense like the standard deviation, yes. And then we have the R squares and the adjusted R squares. So with the summary function, we could get all these things: the standard error of the regressors, the R squares, and the adjusted R squares. So from the multiple regression model, we see that the standard error of the regressions is computed as the square root of the S square of mu hat, where we modify the denominator of the pre-multiplied factor in S of mu hat in order to accommodate for additional regressor, where this the S of mu hat square is it's this is 1 over n minus k minus 1 times the sum of square residuals, where k is the number of regressors that we included in the model. So it's good to know about this formulas, but in a sense, the summary function does this all for us, so we don't have to do any manual computation. So it also talks about the R and the R squares. So in multiple regressions, we have discussed the R square in the previous sessions. So in a sense, in multiple regressions, we want to rely more on the adjusted R square because it's more reliable. As we add more regressors, the R square increases when an additional regressor is added to the model. Adding a regressor decreases the SSR, at least unless the respective estimated coefficients is equal to 0, which is not the case. So in multiple regressions, we prefer the adjusted R square, which is more reliable compared to the R square. But the summary function will give you all of this output. So like in the previous model, the multiple regression model, when we use the summary, it gives us, these are the outputs we get. And these are the significant codes, the significant stars, sorry. So we have the R square and then the adjusted R square. Well, the difference is a bit really small, but we could see the adjusted R square is a bit less than the R square. We could also do this manually, but there is no point in that since the summary output will give us this automatically. So there is no point in doing it manually. So now what we can say about the fit of a multiple regression model of test scores with the percentage of English learners as an additional regression. Does it improve on the simple model included only one? Yeah, of course, yes. So it improves the adjusted R square, which like I mentioned, which is more reliable in this case than the R square. So as already mentioned, R square may be used to quantify how good a model fits the data. However, it is really a good idea to maximize these measures by stuffing the model with more regressors. So we will not find any serious study that that does this. So in a sense, we cannot just say, oh, let's just add more regressors, and then then we rely on the R square to see how well fitted our model is. It's like it doesn't work like that. Instead, it is more useful to include regressors that improve the estimation of the causal effect of interest, which is not assessed by means of the R square of the model. So our R square doesn't tell us anything about causality. In a sense, it just tells us how like it helps to explain how fit the model is, whether it's really the model is well fitted or something like this, but it doesn't tell us anything about causality. So we cannot rely on even the adjusted R square for purposes of causality. Yeah, I think if anyone has any points to add on this part will be good. Kim, you want to add some points on the adjusted R square? Or?
I would say just kind of adjusting R is kind of like compared to the just low R squares. We just keep in mind that this kind of K and n minus K minus 1 by n minus 1. So which is just keep in mind about this one is just kind of compared to the R square. This one is just kind of try to put some more kind of penalized kind of factors based on the number of our regressors. So that's the only thing that we can keep in mind. And also, I think that this part is very important because it says the adjusted R square does not actually explain the how good it fits the data. So it actually have one of the measure to quantify the goodness of fit test, but that does not, our adjusted R square is not everything. We have many different things we need to testing before we look at the model. Maybe in here actually it says about does it improve the simple model to compare to this model? It says yes, and then it actually says about the compare adjusted R square to between the two. But the thing is that this one is actually one way to do that, and then the other second way we can do is maybe in R we actually use the function called ANOVA. Okay, and then we can say about ANOVA model 1 and ANOVA model 2, and then we can actually calculate the chi-square in the different degree of the freedom. in this case, because the reason why we can use this one is like when we looking at the simple model is like this, right? Beta 0 plus beta 1, beta 1, and then student ratio, right?
Yeah.
And then the other model is beta 0 plus beta 1, and students teacher ratio plus beta 2, and percent English, right?
Yeah.
So what you can see about this one is compared to this simple model and this model, you can see that the simple model is what we say about the nested within this second multiple model. Because when we looking at these two model, actually assuming that maybe second our multiple regression model is the kind of like a more like a full model, that means the simple model is the kind of like a nested, because of the full in the second model is just kind of adding the percentage of the English, right?
Yeah. Yeah.
Based on the simple model. So that means our first simple reduced model is the quite nested compared to the second model. So that's the reason why we can use the ANOVA, okay? Here.
Yeah.
Yeah, and then we can compare to the chi-square for that. But the other one is like we have a same simple model, but the thing is when we try to do the next one, maybe not the percentages, not the student ratio. Maybe if we can say about percentage of English, and then maybe math, because in this case, so in this case we cannot say this one actually is this simple model is nested within the second model, because there is no common ground. Because in the simple model we use the STR, but the thing is the second one is that there is no STR in here, right? In this case, simple regression does not nest it, and then in that case we cannot use the ANOVA. Okay.
Yeah.
Yeah. That's
But
the kind of
the F star also might be useful for the like to look at the how the goodness of fit.
Yeah.
Mm.
So, cause in here the reason why I actually explain about the ANOVA is ANOVA calculate the chi-square by using the ANOVA test between the two model. That is another way of the test to test for the fit, goodness of fit. But the thing is, this kind of ANOVA can be used both model actually kind of a nesting relationship. If there is a no kind of there is a no nesting relationship between the two, maybe what we can do is we just compare to the R square or adjusting R square. Or the other thing we can do is maybe I hope that we can explain this one later, but the IKK inferior criteria or Bayesian inferior criteria, AIC and BIC score gonna be another way to compare those two one. And also we can compare about the log likelihood, which is the -2 is, and then I don't know what's the inside is kind of a y1 minus y2, I guess. So these are the kind of a way to do that. So if we like this in this section, if we both model actually have a nested, ANOVA can be used to measure the which one is the much better fit. But if we have a two different model does not nested to each one another, In that case, we can compare R-square or maybe AIC or BIC factor or sometimes log likelihood. So that's the kind of things that I want to talk about. So
yeah. Thanks for that clarification.
yeah.
So now we look at the assumptions, like we mentioned. So we have seen the first three assumptions in chapter 4. So now we are adding the fourth assumption, which is the no perfect multicollinearity, which is in a sense like perfect multicollinearity happens when we can sort of one of the regressors is a sort of an exact linear function of the other. We could sort of form some linear combination of one regression with the other regressor, one regressor with the other. Then we have a problem of perfect multicollinearity, which will sort of make our OLS estimators to be biased. So it's multilinearity. Collinearity means that two or more regressors in a model, in a multiple regression model, are strongly correlated. If the correlation between one or two is its regressors is perfect, that is, one regressor can be written as a linear combination of the other, we have a perfect multicollinearity. So this will make our OLS estimators to be biased. So we have an example where like how does R treat it? Like as in theta and R also, it automatically drops it. It automatically drops the redundant regressor. It does that automatically. So in a sense, we could say it's not a problem because any of these softwares will just automatically delete the other one. So which makes life easier for us. So if we include any variable that is if there is multicollinearity in our model, this particular statistical software we use will automatically drop one of them. So LM will produce the warning in the first line of the coefficient, one not defined because of singularity, and ignores the regressor, which is assumed to be a linear combination of the others, or the one which is redundant. So here he gives an example where we create another variable called the fraction of English learners, which is in a sense it's a linear combination of the percentage of English learners. So the fraction of English learners is just like the English learners divided by 100, which is a linear combination of the English learners. So when we run this model, it gives us this warning. It says one not defined because of singularities, and then it drops it completely. It drops it. So it's saying that if we are to compute it by hand, we'll have the same problem as well, because that's the formula for beta 1. It's the covariance between x and y divided by the variance, and in this case the variance of the fraction of students learning English will be like a constant. So the variance of a constant, it's like 0. So division by 0 will not be allowed. So in this case, this will be like sort of undefined. If we were to do it manually as well, it will be like undefined. So it's looking at two other examples where we have this one we work with dummy variables, where we define this that a school has the like NS attribute when the school's average student-teacher ratio is at least 12. So like NS is 0 if student-teacher ratio is less than 12, and it's 1 otherwise. So when we add the corresponding column to the data and estimate, the model will have will have a multiple linearity problem. Mainly because we'll not, the main thing is all the NS will be 1 because there is no school which has a STR of less than 12. So all the NS will be 1, which will be sort of a which will be a replicate of the English students learning English. Yeah, so when we estimate, the model will have something like this, and it will automatically drop the NS. So this this error is mainly due to how we structure this NS variable. So the way we construct the variable is it's not correct. So because of that, we have this multiple linearity problem. So it's like this is an example where we made logical mistake when defining the regressor NS. Taking a closer look at NS, the redefined measure of class size revealed that there is not a single school with a student-teacher ratio less than 12. So NS is like 1 for all the observations, which in a sense is like this. We have the intercept is equals to lambda times NS, which is like this, and the lambda is like equals to 1. So we have another case where we have like a dummy variable trap. So I think we have a dummy variable trap when we include too much like dummy variables alongside with the intercept. Like we have all these dummy variables. We have the north. We created a dummy variable for the north, for the like the west, south, and east. So when we include all this, since the regional the regions are mutually exclusive for every school, I is equals to 1 to n, we have like north plus south plus west plus east is equals to 1. So if we include all this model and estimate, we'll have a dummy variable trap. So we could have, so we have two options. It's either we drop the intercept and estimate this model, including all the dummy variables we have created, or we drop one of the dummy variables. And the dummy variable that we decide to drop doesn't really matter, but we have to drop one of them. We cannot include all these 4 dummy variables and the intercept as well. Since then for all the observations, I is equals to 1 to n, the constant term is a linear combination of the dummies. So in this case, this will automatically give rise to the problem of dummy variable trap. So it gives an example of this. So when we do this, like R did previously, it drops the is dummy variable. It drops the is dummy variable. So if we had dropped like the not dummy variable, the results will still be fine. Yeah, the results will still be fine. Or if we had dropped the intercept, the model would have, the estimation would have gone fine without any issues. So notice that R has resolved the problem on its own by generating and including dummy variables direction for north, for south, and east and west. Sorry, but omitted the direction on east. Of course, the omission of every other dummy variable, dummy instead would achieve the same. So it's like given us how we'll explain the direction, how will you explain the sort of the outputs. It's like for example, the coefficient estimate for on direction north states that on average test scores in the north are about 1.61 higher than those in the east, and then sort of the same explanation will go for the ones in the south and also the west. So like in a sense, dropping one of the dummies will help us to explain the ones we have in the model relative to the one that is dropped. Yeah, it gives the last example, which is the last example consists the case where a perfect linear relationship arises from redundant regressor. Suppose we have a regressor like the percent of English speakers. And then we set that percent of English speakers as 100 minus the percent learning English. This becomes redundant since the percent of English speakers and the percent of English learners are virtually saying the same thing. So if we include this new variable, the percent of English speakers in the model, it will have a multicollinearity problem. So we have the issue of where we have the like imperfect multicollinearity, where there is a multicollinearity, but it's not like perfect. So it occurs when two or more of the regressors are highly correlated, but not to the level of being perfectly correlated. So the problem with imperfect multicollinearity is that it could imply, it implies that one or more of the regressor coefficient will be sort of imprecisely estimated. Basically, that is what it implies. So it will not necessarily lead to a bias in our OLS estimators, but it could lead to some imprecision of one of the estimates. So when and why is imperfect multicollinearity a problem? Suppose we have the regression model, as in this case, and we are interested in estimating beta 1, the effect of the effect on yi of a 1 unit change in x1 while holding this constant. So if this x1 and x2 are highly correlated, then OLS will struggle to give a precise estimation for beta 1. So beta 1 will still be a consistent and unbiased estimator. Beta 1 hat will still be a consistent and unbiased estimator for beta 1, but it has a very large variance due to the inclusion of x2 in the model. So it's like trying to give the mathematical explanation for this. So basically, in sum, undesirable consequences of imperfect multicollinearity are generally not the results of logical errors made by the researcher, as in the case of perfect multicollinearity, but are rather a problem that is linked to the data set used, the model to be estimated, and the research question at hand. So then it gives some simulated examples. But if anyone has any thoughts on this imperfect multicollinearity and wants to share it.
Yeah, actually in here, no, hold on. In here, no. Could you stay still?
Yeah.
Yeah, in here is the most important one, because when we have a sample size, like a bias and variance trade-off, this one is already talked about in the previous chapters about the like a sample size is small, we have to make a decision about which one we have to choose, higher variance or maybe reduce the biases. So that means by including the many regressors, we can try to find the most fit the model fit into the data, or maybe using the few regressor, which means that we don't have a optimal model but less bias kind of things. Like a few regression means like a more like a less dimension kind of model, like a more smoother line kind of process. So we have to thinking about the maybe sample size is small. It is gonna be matter of the kind of reflecting the higher variances or reducing the variance bias gonna be the problem. So that trade-off should be keep in mind. Especially this one might be happen when we have some kind of a very in-depth interview survey, and then we only have a very few sample size. But the thing is, we have too many regressors in added into that model. We have to thinking about do we have to reduce our regressors to reduce the dimensions, to reduce the bias, or maybe by including all of the regressors and then try to fit the model. But the thing is, when the sample size is small, but if you include too many regressors into your model, that might have a kind of a highly overfitting of the model problem, which means it can successfully explain the our observations. But the thing is, that does not always true, because our sample size does not mean that it always perfectly reflect our entire populations. So in that case, we have to think about this kind of a trade-off, especially for the sample size is small. Like our rule of thumb is maybe sample size is less than 50 or less than 100. In that case, we have to think about these kind of a trade-offs. Okay.
Yeah.
And then also another thing we have to thinking about here is in this chapter, in these sections, the author just kind of simulating the model. But the thing is, let us thinking about in the previous model, like our English score, like a beta 0 and beta 1 STR, and beta 2 and percentage and EL. In that case, maybe what if we can adding another thing for the beta 3 is income, for example. So maybe if there is a kind of some students have a highly income household.
Yeah.
In that case, there might be the highly possibility for their students already learn a lot about the English before they going to the study. So that means these two gonna be the highly correlated to each other. So in that case, we have to think about maybe when we try to testing about the income versus percentage English speaking students, or maybe we can say about the maybe beta 4 is percentage parents foreign, English speaking parents. So
like the parents, parents.
Yeah, maybe if the students have parents who speaks English very well, or maybe if the students' parents, one of the parents or both parents are come from the English speaking countries. In that case, there is a higher correlationality with the percentage of the English speaking students, right? So in that case, when we testing about the correlations, like a percentage of the parents versus percentage of the English speaking students, these gonna be the highly coefficients, like more close to 1, okay? Or not the better than 1, close to 1, right? In that case, we have to thinking about that there is any kind of a multi-collinearity problem between those two variables. So another thing in R, I think you guys already know that we can testing in this case like an imperfect multi-collinearity problem. There is a function called VIF, variance. I think this one is a variance inference factor calculation. So I think that when we testing the VIF score, factor score is more than 5. That means that variable gonna have a multi-collinearity problem. Okay.
Yeah.
Yeah. So we can testing this one too. Yeah. Because
Yeah.
in this example, actually, just kind of a very hypothesis case studies, like simulating the just kind of a model, which is the author is very poor at the kind of setting the example for the actual real world cases. But we can thinking about the, as I just said, we can thinking about the maybe what if we can add in the percentage of the parents who are native English speaker.
Or also maybe the level of
Yeah.
education of the parents.
Yeah, so those might have highly correlated with the percentage of the English speaking students in the class. So in that case, we have to testing that VIF factor, and then that VIF factor is more than 5, that we can consider as there might be the multi-collinearity problem between that variable. So in that case, we have to thinking about the deleting that percentage of the English speaking parents into our model. We have to choose the one of those two variables.
Yeah. Or else the LM function will do it for us automatically, something like this.
Yeah, right, correct. So that's the kind of thing. So because what you say about the imperfect multi-collinearity means we are very suspicious. We have a suspicion about some variable have a multi-collinearity problem, but we are not make sure if there is a multi-collinearity problem in it. There is a way to calculate things. So that is actually VIF function, like a variance violation factor testing. Okay, through that testing, we can testing that VIF score value, and then that VIF value is the more than 5, we can say that that variable has the multi-collinearity problem.
Yeah.
That's it.
Yeah, and the final part is just like talking about the distribution of the Euler estimators in a multiple regression. So in a large sample distribution of the beta, the predicted betas, like large sample, we are saying at least it's greater than 30 or maybe greater than 50 or something like that. If the least squares assumption in the multiple regression models, like 1 to 4, it's satisfied or it holds, then in large samples, the OLS estimator, beta naught hat, beta 1 hat, up to beta k hat are jointly normally distributed. We also say that their joint distribution is multivariate normal. Furthermore, each beta j hat is distributed as normal, with mean being the true, with normally distributed with mean of beta j and a variance of sigma square. So here, basically what it's saying that, if our sample size is large enough, and then these 3 assumptions hold, we could generalize that our estimators will be jointly normally distributed. Basically, that's what it's trying to explain here, and it gives a simulation of this in R. And so that's what it plots here. Yeah, and we could see here better even in this plot.
Yeah, it's a kind of literally about the jointly distributed is when we looking at this side or this side, it is always follows this kind of a
Yeah, normal distribution.
normal distribution.
Yeah.
By combination of the beta 1 and beta 2, we will have these kind of things depending on their changes. That's the reason why we have this kind of a three-dimensional kind of plots. But when we have more than three regressors, that in that case we cannot do all these kind of things. But
Yeah, we
we
cannot be
still,
precise,
but still we can see that we can just assume that there is a jointly distributed kind of a curve gonna be happen in that hypothetical kind of a high hyperdimension space, vector space.
Yeah. Yeah, that's it. I think that's it for this chapter.
Okay, good. Yeah, thank you very much. And then yeah, it's very helpful. And then yeah, so yeah, and then so who wants to do the chapter 7 then? Maybe.
You look at the sheet.
Yeah, we have a seat, right? So
Let me
how?
see. Chapter 7 is me.
Yeah,
Okay.
yeah. So
Okay. Yeah. So I will, yeah. So we can cover the chapter 7 next week, and then yeah. So I will see you all next week then.
yeah.
Sounds good.
Okay. So see you next week.
Yeah.
Bye guys. Thank you.
Yeah. Bye bye.
Yeah. Bye. Thanks.
Yeah.